define the belief propagation algorithm as a message passing algorithm over a fairly general data structure called a cluster graph. And we showed that if the cluster graph has certain properties, then so does the belief propagation algorithm. What we're going to do now is we're going to look at a special case of the belief propagation algorithm where we pass messages not over a general cluster graph, but rather over a data structure called a clique tree, which, as we'll show, is a special case of a cluster graph. But interestingly, when we pass messages over a clique tree, we can show that the belief propagation algorithm has much stronger performance guarantees than it does over the general graph. And specifically, we can show that not only can we get convergence much faster, we can also get convergence to the exact answers for probabilistic inference.
So let's consider the case of passing messages tree, and I'll start with the simplest kind of tree, which is just a chain. So in this case, we have a chain A, B, C, D, E, and we're going to assume that this is an undirected MRF or CRF, and so we have and for simplicity, we're only going to consider the pairwise potentials without loss of generality, and so we're going to have just pairwise potentials here that, for example, in the cluster AB, we're going to have the pairwise belief over the pairwise potential over AB, and so on. So, so here we have psi1, psi2, psi3, and psi4. So now let's think about the message passing process. And we're going to start passing messages from the left. And so cluster the message to cluster 2, and since there's no incoming messages at this point, the message that gets passed is simply the sum over A of psi1 of AB, and that's a message whose scope is B. Now we're going to have cluster 2 take that message and pass the message to cluster 3. And so now it's taking its own potential, psi2, and multiplying in this message into this. And the result is a factor over B and C, and we're going to sum out over B because we only want to restrict to the scope C, which is the shared scope between cluster 2 and cluster 3. And so delta 2, 3 is this message over here. Now we're going to pass messages one more time, all the way down to the end. And so now, again, we're taking delta 2, 3, multiplying it with psi3 that comes from there, and that gives us a message over scope D, which gets sent to cluster 4. You could also pass messages in the other direction. So this, for example, would be what would happen if we pass messages from cluster 4 to cluster 3. Regardless of when that message gets passed, there's no other messages that cluster 4 would multiply in when sending a message to cluster 3, because whether it got the message from 3 or not, it's not going to multiply that in. Because remember, you only send the cluster a message that doesn't involve messages that you received from it. And so in this case, the message that you get is the sum over E of the factor psi4, which we get from here. Passing messages in the other direction again, we see that the message that cluster 3 passes to cluster 2, which is delta 3, 2, involves psi3, and this message over here. And finally, exactly the same idea. These are the messages that gets passed. Okay. So one important property that you have when you run message passing in the way that we just showed is that somewhat surprisingly relative to what we've seen before, the resulting beliefs that you get are correct. And let's convince ourselves of that relative to cluster 3. And so in the order that we defined, cluster 1 passed delta 1, 2 to cluster 2, which was then used to define delta 2, 3. At the same time, we had delta 4, 3. And so the beliefs that we get here are the product of psi 3 times delta 2, 3 times delta 4, 3. Let's unpack each of those messages. So delta 2, 3, as we remember, was defined here. And so we're going to rewrite what delta 2, 3 is as the summation over b of psi 2 delta 1, 2. And similarly, we unpacked delta 4, 3 to get using this expression that we have over here, right there. Now we're going to do one further level of unpacking. And we're going to remind ourselves of what delta 1, 2 is, which is as defined over here. And so that gives us this expression over there. And now look at what we have. We have a product of all of the 4 initial factors in the network: psi 1, psi 2, psi 3, and psi 4. We have a summation over all the variables that are not in cluster 3, which are A, B, and E. C and D are in that cluster, so we sum out over everything else. So already we see that we have a product of factors marginalized out where we marginalized out irrelevant variables or unnecessary variables. So this is really reminiscent of variable elimination. And if you recall, when we talked about the correctness of variable elimination, we said that variable elimination is correct as long as when you sum out a variable, you first multiply in all factors that relate to it, that involve that variable in their scope. So let's convince ourselves that that is in fact what's going on here. So let's look first at the variable E, and when we sum out E, we're multiplying, we're only involving psi 4, but that's okay because only the cluster 4 has E in its scope. Here we're summing out A, and once again, only psi 1 involves A in its scope. Here we're summing out B, and really there should be parentheses here. They were there implicitly before. And so you can see that when I'm summing out B, I've involved psi 2, which involves B in its scope, as well as what was left over from summing out psi 1, which is the other factor that has B in its scope. And so you can see that I've marginalized out the variables in a legal order, multiplying in only the expression, multiplying in all of the expressions that I needed to multiply before I did the summation. And so this is a legal order of operations. And therefore, it gives me a correct result at the end. So now let's expand that into the somewhat broader case. We're now going to define this notion called a clique tree. And a clique tree is an undirected tree, kind of like a cluster graph was an undirected graph. So in this case, it's a tree, such that, once again, the nodes are clusters. And once again, we have edges between the clusters, which are called subsets. And in this case, whereas before we had that the subset needed to be only a subset of Ci intersection Cj, it could be smaller, it could be equal, or it could be smaller. Here we're going to require that the subset is actually the intersection of the 2 adjacent clusters. So now let's go and understand what properties the clique tree that we showed has as a special case of a cluster graph. So for a cluster graph, we had the notion of family preservation. And the reason that we had family preservation is because if we have a set of factors phi, we needed to take each phi k in phi, and we needed to assign it to some cluster so that each piece of information that we have is represented somewhere. And the factor needed to be such that the cluster could accommodate its scope, so that the scope of the factor was a subset of the set of variables in the cluster. And the same requirement holds here because a clique tree is a special case of a cluster graph. So that we have that for every factor phi k, there must exist at least one cluster whose scope is big enough to accommodate that factor. The second property that we had in cluster graphs was the running intersection property. And let me clarify that the property that we see here is the cluster graph variant. We're going to make it specific to clique trees in just a minute. So the cluster graph variant told me before that for each pair of clusters, Ci and Cj, and a variable x that is present in both of them, there needed to exist a path between Ci and Cj for which all clusters and subsets contain x, and it needs to be unique. So what does that mean in the context of clique trees? Let's assume that we have C7 containing x and C6 containing x. And the cluster and the running intersection property says that there needs to exist a path between them for which all clusters and subsets contain x. Well, there's only one path in a tree between C7 and C3. It's this one. And so what that property now tells me is that x has to be here, 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 and here. Because otherwise the running intersection property is going to be violated in this case. So that means that in the context of trees, the running intersection property can actually be written much more simply. It can be read as saying that for each pair of clusters, Ci and Cj, and a variable x in their intersection, each cluster and subset and the unique path between them must contain x. And so this is just the instantiation of running intersection property to the context of clique trees. So now let's look at a more complicated clique tree. This is the clique tree that corresponds to the network that we previously used to demonstrate variable elimination. This is the elaboration of our student network. And so this is, unlike the previous example, this is actually a clique tree for a Bayesian network as opposed to a Markov network, but as you'll see, there's really no difference. So here we have a set of factors. In this case, the factors are CPD. And because of the family preservation property, we can be assured that each factor must be assignable to some clique. And so here we have P of C and P of D given C are assigned to this clique, P of G given ID, P of I and P of S given I, and so on and so forth. So each of the CPDs that we have is assigned to one and exactly one of the cliques in this clique tree. And we can convince ourselves that this tree satisfies, for example, the running intersection property. So let's look, for example, at the variable g. The variable g exists here, it exists here, and sure enough, it exists here, 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 and here. And you can similarly convince yourselves of that for any of the other variables in this clique tree, that the running intersection property holds for that. Let's look at what message passing looks like for this more elaborate clique tree. So it's a little bit, only a slight bit more complicated. So here we have, for example, delta, so it's not even that much more complicated. So here's delta 2,3, for example, and delta 2,3, which is the cluster between, which is the message pass between cluster 2 and cluster 3, takes psi2, which is the product of the factors assigned to this clique. Actually, there's only one in this case, so it's only P of G given I and D. So that's psi2, multiplies it with the incoming message delta 1, 2, and sums out over D. The only slight difference between this and the previous example that we had is that here, for example, when cluster 4 passes a message to cluster 3, we can see that over here there's two variables, J and L, both of which must be summed out in order to produce the message over the requisite subset. Now, we defined the running intersection property. One of the really nice aspects of the running intersection property is that it, by itself, together with family preservation, suffices to prove the correctness of message passing in a clique tree. And the reason for that is the following. if, so let's consider a variable x over here. And let's, and what we want to prove is that if we eliminate x at some point in the tree, at some point in the message passing process, then we have multiplied in all factors that involve x. And so here we have, for example, x here, and by the running intersection property, we have the x is here and here as well, and on the subsets. And let's imagine that x is eliminated on this edge. That is, the message that's passed from C3 to C5 the message that's passed from C3 to C5 doesn't involve x, and so x must be summed out at this point. Well, at this point, we know that x cannot be here. Because if x were in C5, then it would also be in the subset. If x in C5, then x is also in S35, at which point x wouldn't be eliminated. And the reason we know that if x is in C5, then x is in S35 is because of the running intersection property. So the running intersection property relates the structure of the graph to the structure, to the time at which variables are eliminated. So now let's convince ourselves of the correctness in this slightly more complicated example that we've seen satisfies the running intersection property. Here, once again, we have psi1, which is the product of these two factors, psi2, which is this one, psi3, which is the product of these two factors, psi4, psi5. And once again, let's, for example, consider what we get at cluster 3, and we can see that we have multiplied in all of the potentials, psi1, psi2, psi3, psi4, and psi5, and that we have eliminated all of the variables except for GSI. So here we've eliminated C, D, J, L, and H, leaving us only with the variables GSI, which we want to keep. And we can similarly convince ourselves, as we did before, that when we eliminate a variable, we've multiplied in all of the factors that involve that variable. So to summarize, we can take belief propagation and run it over a cluster graph that happens to be tree structured. And when we do that, it turns out that the computation that we're running is actually a variant of variable elimination. And because of that, the resulting beliefs are guaranteed not only to be calibrated, but to actually be the correct marginals of the unnormalized density p tilde phi. So previously we defined the clique tree algorithm, which is just the belief propagation algorithm run over a graph that happens to be a tree. As it turns out, we can exploit the aspects of the tree to greatly improve the computational behavior of this algorithm, not just its correctness, which is what we showed before. So let's go back to our message passing in this very simple tree, which has just these 4 clusters, A, B, B, C, C, D, and D, E. And let's see what the messages do. So here is the message delta 1, 2, which is the message that's passed on this edge. And here's the message delta 2, 3, and so on. And these are the 6 messages that we have. And now we can notice one very important property. Delta 1, 2, once computed, never changes. So you get instant convergence of delta 1, 2. Once you compute it for the very first time, you're at convergence. Now what about delta 2, 3? Well, that depends on when delta 2, 3 is passed. If delta 2, 3 is passed first, before cluster 2 gets a message from cluster 1, then once it gets that message, things might change. But if cluster 2 is clever, it's going to wait. And it waits until that message is passed. And once that message is passed, since it doesn't change, delta 2, 3 doesn't change either, ever, if it's smart enough to wait. What about delta 3, 4? Delta 3, 4 needs to wait a little bit longer because it needs to wait for delta 2, 3. But if it waits for both delta 1, 2 to be passed to cluster 2 and delta 2, 3 to be passed to cluster 3, then now that it sends delta 3, 4, delta 3, 4 doesn't change either. So delta 2, 3 has to wait for delta 1, 2, and delta 3, 4 has to wait for delta 2, 3. But assuming it waits, then convergence is achieved in a single message passing step. Now, there's nothing magical about going left to right. If you go right to left, you get the exact same behavior. So here you have that this one converges instantly. This one, you need to wait for delta 4, 3. And this one you need to wait for delta 3, 2. But again, assuming you wait, then the messages converge in a single step. And so we can compute all of the messages in this entire tree in one pass in either direction. One pass from left to right and one pass from right to left. In the context of chain structures like this one, this actually has its own name. So for chains, you might see this under the name forward-backward algorithm. And it's very commonly used in things like hidden Markov models and other similar chain structured representations. And so the point is, the total effort that we had to compute all of these messages is just one message passing step in each direction. One from left to right and one from right to left. And the result of that, remember that once all messages have been passed, we have beliefs that are correct, beliefs that represent, that are marginals of p tilde phi. And so we've computed all of the marginals of all of the clusters in this graph in sort of two sweeps over this clique tree. And so more generally, as we said, one CI receives a final message from all of its neighbors except for CJ if it waits to send the message to J until it receives a message from everybody else, then that message, delta ij, is also final. So if these are final, this is also final. Can you always find a message passing order that will achieve that goal? I mean, maybe you everybody ends up waiting for everybody else and they all get stuck and they never send anybody any messages. The point is that you could always start, because the message from a leaf is always immediately final. And once the message from a leaf is finalized, then you can send the message from the parents of the leaf, and so on and so forth. And because this is a tree, it's guaranteed that you will be able to find a legal message passing order. And if we pass the messages in the right order, then we only need to pass 2k minus 1 messages, where k is the total number of clusters. And why is that? Because if you have a tree over k nodes, in this case k clusters, then there's k minus 1 edges. And since each edge has a message in both directions, so we have k minus 1 messages, k minus 1 edges, and therefore 2 k minus 1 messages, 1 in each direction. Let's look at a couple of message passing orders to see which ones are going to work and which ones aren't. So we can start with any leaf works. So say we start with, C2. Once C2 has passed its message, what other clique can pass its message? Well, C3 can't pass messages yet, because it's still waiting for messages from all sorts of other guys. So we have to go to another leaf. For example, C1. C1 can pass a message now. Neither C3 nor C4 are candidates for message passing yet, because each of them is still waiting for another message. But C6 can pass a message, and now we have the option of activating C4. C4 can now send the message to C3, because it got everything except the message from C3 before. C7 can say pass a message to C3, and you notice there is a lot of arbitrary decisions on how I ordered this. I could have used C5 next. And now C3 has the option of passing a message to C5. And notice that at this point, everyone has received all of the messages, or all of the messages but one. And so now we can start passing in the other direction. So C5 can pass a message to C3. C3 can pass a message to any of C2, C7, or C4. And at this point, C4 can pass a message to both C6 and C1. What is an example of an illegal message passing order? So for example, if C1 passes a message to C4 and C4 jumps the gun and says, yay, I'm going to send the message to C3 next, that is an illegal message passing order, because C4 does not yet have all the information that it needs to pass a message to C3. It's still waiting for a message from C6. So that's not a good ordering. Clique trees have other very elegant computational properties that make them a useful data structure. So let's think about the kinds of queries that one can answer using clique trees, and some of these are fairly obvious, but others are a little bit more subtle. So imagine that we wanted to answer a posterior distribution query on either a single variable or a set of variables that appear together in a clique. Well, in this case, you could take any clique that contains all of those variables and sum out the variables that you don't care about from that clique to get a posterior over just those variables. Now remember that that posterior is p tilde phi, it's an unnormalized measure, so in order to get the normalized measure, you actually need to renormalize. Now, you could also do something a little bit more clever. You could say you wanted to introduce new evidence regarding some variable and query another variable. So this is a form of incremental inference, where you've already calibrated the clique tree, and now you say, ooh, wait a minute, I made another observation. Let's see what happens now. So it turns out the clique trees are really good for that. And so we're going to divide this into two cases, the easy case and the slightly less easy case. So imagine that we want to query a variable x that appears in the clique with my new evidence z. So here is my clique, and here is z, and here is x, and I want to figure out what the posterior of x would be if I further observe z. Well, this is actually really easy because what I have here is p tilde phi of, let's assume for the moment, just z and x. If there's other variables there, it doesn't change anything because we could always just get rid of them. We can now condition or reduce the clique. So this is a clique reduction by just restricting attention to the entries that are consistent with my evidence z. And then I end up with p tilde phi of little z comma x. And in order to get a posterior, I can sum out the relevant variables and renormalize. So I can do incremental inference. Okay, well, that's the easy case if the two variables are together in a clique. What about a somewhat more elaborate case where I introduce the new evidence and I query a variable that doesn't appear in the same variable, in the same clique as z? So using an example, let's imagine that what I did is observe evidence on A, and I want to query, say, E. Actually, let's do a different example. Let's imagine that I want to query D. Well, in this case, I can do the following. I can multiply this indicator function, or what we call this reduction of the factor, into a cluster that contains the evidence. So in this case, we're going to multiply in the indicator function of A equals little a, which corresponds to removing all entries in cluster 1, in the beliefs of cluster 1 that are not consistent with sorry, not into the beliefs. We multiply it into psi 1, removing all entries that are inconsistent with that. So now, what happens when we change psi 1? imagine that we were doing this entire computation from scratch. That is, forget everything that we did before and think what would happen to this model in the hypothetical case that we were passing messages with a new psi1 instead of the old psi1. Well, some messages would change. Which messages would change? Delta 1, 2 would change because psi1 changed. Delta 2, 3 would change because delta 1, 2 changed. Delta 3, 4 would change, but we don't care about delta 3, 4 if we're interested in this belief over here. What about other messages? Delta 4, 3 doesn't change. Neither does delta 3, 2. Neither does delta 2, 1. And so only a subset of the messages in the clique tree change as a result of this change, which means that we can reuse at least half the messages, if not more, in computing our beliefs about, in this case, cluster 3. And the only messages that we need to recompute are the messages that are along the path to a clique that contains the variable x that we want to query, which in this case is cluster 3. So to summarize, if we have a clique tree with k cliques and we pass messages in a careful order, which means that we start at the leaves and propagate inwards, then we can construct an ordering such that 2k minus 1 messages suffice to compute all of the beliefs in the clique tree, which means we get a posterior over every single variable in the model. Contrast that with the computational cost of running variable elimination n times to compute posteriors in n different variables. Here, you get a considerable computational savings, in fact, a computational savings of order of the number of variables. And so what we can do is we can compute all of the marginals at only twice the cost of variable elimination as opposed to n times the cost of variable elimination. And we've also shown that by caching or storing the messages, we can reuse inference, for example, in the context of incremental queries, which provides us with a useful data structure to keep updating as we obtain additional evidence.